Hey, business calculus students. I've been fielding some questions, and I think maybe I can clarify some of this by re-recording the lesson that I had posted and try to make things a little bit clearer for you, because the material here, the actual work shouldn't be difficult, but maybe making the connection is going to be a little more difficult. So let's start out by talking about rates of change and what rates of change are and what they aren't. A rate of change is basically a change in some kind of output of a function. And right now I'm just going to use the word output. And you can think of output as the y variable. So the change in the output of a function based on how the input changes. And you could think of input as the x. And in the formulas, a lot of times we use Greek characters. And in Greek characters, change is represented by a triangle or a D, both of which are Greek characters for delta, and delta represents change. So we're talking about delta y over delta x, which for a lot of you will look a lot more familiar if I write it as y2 minus y1 over x2 minus x1. And that should look more familiar to you because that is the slope m. So the rate of change is basically simply a slope. So with that in mind, let's try to talk through the next example and thinking about how slope ties up with what we're talking about. So suppose we take a trip from Nashville driving east, which means we're coming from Nashville back to East Tennessee, and every half an hour we're going to make a note of how far we traveled with the results that are listed in this table below for the first 3 hours. The function that we're interested in here is the one that has the rule n of t is equal to the distance from Nashville at any particular time t. So, for example, using the table, we are to find, first of all, what is n of 0. In other words, how far had we gone when we actually began the trip, when 0 hours had elapsed? And n of 0, you'll see here, we had actually gone 0 miles. Because when we first started our trip, no time had elapsed, t equals 0, and our distance, since we hadn't started our trip, was 0 miles. N of 1 says, basically, how far have we gone after 1 hour? And to understand that, we look at this entry in the table, and after 1 hour, we've been traveling 1 hour, and we have driven 55 miles. And at the end of 2.5 hours, similarly, we have driven 124 miles. And then the next question we have is, what was the distance traveled during the second hour? And the second hour is actually from hour 1 until hour 2. And the distance we had gone was, at the end of hour 2, we had traveled 104 miles. And at the end of hour 1, we had traveled 55 miles. So for that 1 hour, which was the second hour of the trip, in the second hour of the trip, we had traveled 104 minus 55 miles. which means that we had traveled, I believe that's 49 miles. You can check that on your calculator. And similarly, in the first hour, even though that's not asked for here, in the first hour from the time we began at time 0 until 1 hour had elapsed, we had gone 55 miles. So kind of to get into what the average rate of change is here, during the first hour, our average rate of change was 55 miles per hour. Meaning that in 1 hour, we had driven 55 miles. And that is our average rate of change. So here, average rate of change, in this particular problem, we're talking about the rate of change of distance as it is defined by time. So it's going to be the change in distance over the change in time. Our 55 miles an hour means that the change in time from 0 to 1 hour was 1 hour, and we had gone 55 miles. That also means that during our second hour, we had gone 49 miles, and our average rate of change was 49 miles per hour. So here, the average rate of change we're talking about is actually what we think of as speed. That's what speed is how far did you go over a set amount of time. And looking at our entire 3 hours, let me move the table, we see that over the course of the entire 3 hours, we went 138 miles in the time of 3 hours. And this might, since we're talking about distance and rate, this might remind you that since distance is equal to rate times time, what that means then is that our average speed is distance over time. Because distance equals rate times time, if we want to know the average speed, then average speed is a rate. And it's a rate of change. So if you solve this formula for rate, then rate is equal to distance divided by time. R equals D over T. So the average speed of the whole trip would have been our speed at 3 hours, or our distance at 3 hours, minus our distance at 0 hours, and that would have been the entire trip for that entire 3 hours. So therefore, our distance was 138 miles divided by 3 hours. which was 46 miles per hour. So this was our average speed, which is a rate of change. So we can use this approach to determine average speed which is a rate of change, over any time interval. Remembering that in this case, we're still talking about slope, and the slope is the difference between 2 points, and at the 3-hour mark, we had gone 138 miles, whereas when we started the trip, we had gone 0 miles. So this is simply a slope formula. This is the distance change. And this is the time change. So continuing our discussion of the average rate of change, in this case we're talking about speed, with the rate of change in distance as determined by the amount of time that's elapsed. Then if we want to determine the average speed during the second half hour of our trip, then we will begin by thinking about what happened at the end of the first hour of our trip. And at the end of the first hour of our trip, we had gone 55 miles per hour. And at the end of the first half hour of our trip, 1/2 hour has elapsed. And at the beginning of that half hour that elapsed, we had gone only 30 miles per hour. So 55 miles minus 30 miles means we have traveled a distance of 25 miles in that half hour. And 25 miles divided by 0.5 is equal to 50, and once again, that's miles per hour. During the time of our trip when we're talking about from the first half hour to the end of the first hour and a half, you see here that we've actually traveled 1.5 minus 0.5. We've traveled for 1 hour. And at the end of that 1.5 hours, we had gone a total distance of 80 miles per, or 80 miles, not miles per hour. We had traveled a distance of 80 miles. And at the end of the first hour, half hour, we had gone 30 miles. Then that means that we had traveled a distance of 50 miles over the course of 1 hour, which is, of course, again, 50 miles per hour. Our speed, or our average speed, during hour 1 to hour 2 means that from the end of the second hour, from the end of the first hour, we have traveled for once again 1 hour. And at the end of 2 hours, we've gone a total of 104 miles. Whereas at the end of the first hour, we had gone 55 miles. And we've already discussed that 104 minus 55 is 49 miles that we traveled in 1 hour. So the average speed, which is the slope of the point 2,104 to the point 155, that average rate of change was 49 miles per hour. Similarly, if you want to know your average speed from the end of hour 1 to the end of hour 3, at the end of hour 3 from the beginning of hour 1, we've gone 3 minus 1, or 2 hours. And at the end of 3 hours travel, we had traveled 138 miles. Whereas at the end of the first hour, we had traveled 55 miles. And 138 minus 55 is 83 miles in 2 hours. And since 83 divided by 2 is 41.5, we had an average speed during that 2-hour time period of 41 miles per hour. And once again, that's the slope from the point 138 to the point 155. So in general, when we're talking about the average speed from time A to time B, at the end of time B, we had gone whatever distance we had traveled in those B hours. And at the beginning, we were at time A, and its output value, its distance, was the time we had traveled in those A miles. And this, once again, is going to be miles because it's distance per hour. But it is also a slope. It is the slope of a straight line that connects up point B, S of B, to point A, S of A. So the average rate of change for any function, it doesn't matter what the function is, what it's describing, what its input and output units are, the average rate of change for any function with respect to x, which x means, of course, that that's its input values, its independent variable values. As x changes from A to B is given by the distance B minus A, or the difference B minus A, over the output for B minus the output for A. So the 2 points that we're talking about here, once again, are B, F of B, and A, F of A. And this is, once again, simply a slope formula. It's for the slope of a line between 2 points. So just to continue with our example, this is a graph of distance versus time for that same table that we looked at in the beginning. And what I'm trying to get connected for you is that at the end of, let's say, our first hour, half hour here, to the end of the first hour, we have had a change in time of a half an hour. And the change in the distance was 25 miles. And that gave us 25 miles in a half hour, which means that our average speed over that time interval was 50 miles per hour. And so on and so on So if we were at the end of the second hour here, and we went to the end of the third hour, that's a change of 1 hour. And you can see that our time was increasing, but our distance was also increasing because we went a positive time and achieved a positive difference. We didn't go backwards. And the distance that we actually achieved in that time was 134 miles. I'm sorry, not 134 miles. My goodness, that's not good. We actually achieved 34 miles because at the end of the second hour we had gone 104 miles, and at the end of the third hour we had gone 138 miles. So that was a distance of 34 miles. So that means that during that hour we only went an average of 34 miles per 1 hour. So we were really slowed down. We must have run into a traffic jam during that time. So as our second example here, we're talking about education spending. And this figure shows education spending in total that's appropriated annually in billions of dollars from the U.S. Department of Education for the years 2009 through 2013. And we want to find the average rate of change per year, remembering that this is years. We want to find the average rate of change per year from 2009 to 2013, which means the only points that we're going to be interested in here is this point and this point. So what I want you to focus on is that what we're actually calculating here is the slope of a line segment that connects those 2 points up. And the 2 points that we're talking about are 2009, $63.52 billion, and the second point is 2013, $65.70 billion. And I want you to keep in mind here that the average rate of change only takes those 2 points into account. It doesn't take into account anything that happens in the intervening years. So it can be a very misleading kind of rate of change. So in order to find that rate of change, that average rate of change, we're going to take the point 2009, 63.52, and the point 2013, 65.70, and we're going to calculate a slope, because we're looking at the slope of the line that connects those 2 points. And since your x values always go on the bottom, and we're always going to begin with the last point, the one that's furthest from 0. So that's going to be 2013. So in 2013, from 2009, what has passed is 4 years. And our spending has changed. It has actually increased to 65.70 from 63.52. So that's a change in billions of dollars. And that change, 65.70 minus 63.52, is a change of $2.18 billion. So in the span of 4 years, spending increased $2.18 billion, which was an average of $0.545 billion per year. So it's an average rate of change in spending. And basically we're saying that over the course of the 4 years, that's the average rate of change, which obviously is fairly close to the rate of change from 2009 to 2010. But notice that in 2010 to 11, spending increased sharply. Then in 2011 to 2012, it actually decreased slightly. And then from 2012 to 2013, it decreased even more sharply. And all of those changes actually averaged out to $0.545 billion per year. So on the average, the amount appropriated went up by $5.45 billion, excuse me, 0.545. And 0.545 billion is actually $545 million per year. And that's on the average between the years 2009 and 2013. Now we're going to return to our distance and time concept here and talk about instantaneous rate of change. What your speedometer does on your car is it tells you your instantaneous rate of change at the exact moment that you look at your speedometer. Not at an average time from now until 5 minutes from now, but at right now, this very moment. So in this case, suppose you have a car stopped at a traffic light. When the light turns green, the car begins to move along a straight road. We're going to assume that the distance traveled by that car is given by the function s of t is equal to 3t squared, and t is being measured in seconds, so this function is only in effect here for the first 15 seconds of the trip. After that, the speed may increase or decrease by the person either pressing down harder on the gas pedal or letting up on the gas pedal or pressing down on the brake. What if we wanted to find what the speed of the car was at exactly t equals 10 seconds? So that's the situation we're wanting to discuss here. This is called the instantaneous rate of change. And we're going to use the idea of a limit to try to figure out what instantaneous rate of change is. Because rate of change is an average rate of change if you're going from point A to point B. Now, if we wanted to figure out as close as we could to how fast we're going at 10 seconds, we could figure out our average rate of change, our average speed, when we went from 10 seconds to 10.1 seconds. In other words, over that single tenth of a second interval, how far did we go? And if you use your calculator, S of 10.1, since S of t is 3t squared, S of 10.1 is 3 times 10.1 squared. And that's 306.03 feet. Whereas at 10 seconds exactly, that would be 3 times 10 squared, which is 300 feet. So during that single tenth of a second, we have gone 6.03 feet. And that's 6.03 feet divided by 1/10 means we would have gone in that 1/10 of a second. Our average speed was 60.3 feet per second. Okay? Now, 1/10 of a second is not very long, but it's still not instantaneous. So if we, again, used S of 10 and 10, at the end of 10 seconds, we had gone 300 feet. What if we went even closer? What if we only went 10.01? So we went 100th of a second. So what we're doing is we're saying 3 times 10.01 squared, and that gives us 300.6003.